And welcome to Saturday Morning Physics and today's Walker Family Lecture. I'm Physics Professor Tim Chupp, one of the organizers of Saturday Morning Physics, along with my colleagues Roy Clark, Carol Raybuck, Monica Wood, and her team in the demo lab here at the University of Michigan. And there are many, many more who bring you Saturday Morning Physics. So our staff, our video crew, the live stream that we now have, thanks to COVID, the donuts, all are made possible in part by generous support of our Saturday Morning Physics community, and that's you. Thank you very much. We're also grateful to the Dr. Mary Lois Tiffany Endowment, the Hideko Tomozawa Endowment, the Van Loo Family Endowment, and the Walker family, sponsor of today's event, that makes it possible to bring a distinguished speaker to the University of Michigan to take part in the Saturday Morning Physics tradition. So now I'd like to introduce Diana Walker, who will tell us more about what this means to the family. Thank you for the support for Saturday Morning Physics and for this lecture.
You're welcome. Thank you. Good morning, everybody, and welcome. Not loud enough? Loud enough? Okay. Good morning, and welcome to Saturday Morning Physics. Today is the 7th year that I have the privilege to commemorate my father, James Robert Walker. He was born in Marshall, Michigan, just west of here, of quite meager circumstances, but he knew what he wanted to do with his life, and that was to learn everything he could about electrical engineering and physics, and that's exactly what he did. His diligence and commitment to advanced learning allowed him to be part of some very exciting experiments at his time. And I kind of believe that he did leave his mark on the world of science and industry. One of the experiments that he was part of was in Philadelphia when they worked on detecting submarines with sonar radar. Then he also worked over at Wright-Patterson Airfield Base over here in Ohio, and what they worked on was nuclear energy. And they wanted to experiment and see if nuclear energy would be appropriate for the propulsion of aircraft. That's how long ago that was. He also was able to work here at Ann Arbor, which he loved so much, on the cyclotron when it came to Ann Arbor. During the Second World War, he was called into action again to help work on servo controls, which were very important at the time, and that was at the Excello Corporation in Detroit. It's right at that era when Detroit came to be known as the Arsenal of Democracy. So Detroit made their landmark on more than just the car industry. So my father lived to be 96, and he came to the very first Saturday Morning Physics here. And in 94 was his final lecture here. And how he got by every single week was waiting to sit here just like you guys as inquisitive pupils. So his chauffeur is here today, and she's sitting way up in the audience, and I'd like to recognize her. And that's my mother. Mary Walker at 99, so never give up.
Okay, thanks so much for sharing that, and thank you and welcome, Mrs. Walker, to Saturday Morning Physics again. Thanks, Diana. So now it's my honor to introduce today's lecturer and guest, Ron Walsworth. He is the Minta Martin Professor of Physics and Electrical Engineering at the University of Maryland. He's also the founding director of the University of Maryland's new Quantum Technology Center. Ron grew up in New England, and he attended Duke University and then Harvard for graduate study, receiving his PhD in 1991. His graduate work was on innovations of the hydrogen maser, which was at the time, in many ways, the best atomic clock, and it also provided many studies of fundamental physics at the Smithsonian Center for Astrophysics. Ron stayed at the Smithsonian and became a PI before moving to Maryland in 2019. He's made an amazing number of contributions to a broad range of issues in fundamental and applied science and technology, and he's received a number of awards and recognitions, including the Pipkin Award and a fellowship from the American Physical Society. The title of his lecture is, well, Quantum Tools. And Ron, thanks for traveling to Michigan, where spring comes just a little bit later than it does in the DC area. Ron.
Does my mic work fine? Can people hear me? Great. Let's have some fun on Saturday Morning Physics. Thank you very much, Tim, for the introduction. The Walker family, very amazing, and thank you so much for your generosity over all these years. Mr. Walker's an amazing person, Mrs. Walker, everybody. So I'm here to tell you about quantum tools to explore the universe and help life on Earth. Hopefully you're going to enjoy it a little bit, and we'll see some of these gems showing up a little bit later. I kind of have one basic message, and then we're going to have two big stories. Two stories. The one message is that everything is quantum, ultimately, everything in the universe. We normally think of quantum as being about atoms and molecules, but our everyday objects, dogs, cats, our cells, etc., quantum physics is relevant there, and certainly on the very large scales about our universe, galaxies, the entire universe. Quantum physics is relevant to everything. It's most prominent, and it was discovered and most focused on at the atomic scale, but increasingly quantum effects are found and are identified and are being understood and exploited throughout all length scales and time scales. But what is quantum? Quantum, in the early days, in the early 1900s, about 100 years ago, when quantum theory was being developed, was thought again to be about atomic scale physics. There were certain principles to try to explain experimental discoveries in the late 19th century and early 20th century. There are certain principles which were identified. That fundamental objects and properties are discretized or quantized. They come in certain units. Electrons, you find one electron. You don't find half an electron, etc. In atoms, there are discrete energy states or energy levels that atoms can exhibit. Same thing with charge and other properties. There's interesting dualities that were uncovered. Some things which seem primarily to be particles can also have wave-like behavior. Electrons are particles, but they can exhibit wave-like behavior. We think of light at times as a wave, but it can exhibit particle-like behavior. And the particles of light we call photons, etc. So this wave-particle duality, and also a fundamental uncertainty principle that we can't know everything perfectly well no matter how good our technology is. There's some fundamental trade-offs in certain cases between knowing things like position and the momentum of a particle as it's moving. There were a number of pioneers back there 100 years ago. You've probably heard or read about many of them, people like Schrödinger and Heisenberg and Bohr. And it was a very successful theory. But it led to a lot of musings, most famously by Einstein talking to Bohr about this quantum world, because it led, the theory, though successful in terms of explaining experiments that were measured on atoms and things like this, led to counterintuitive effects and behavior. Things like superposition, that quantum objects can be in a superposition, more than one state at the same time. And entanglement, that the quantum objects can be correlated, even in principle, over arbitrarily long distances. So this led Einstein to be very unhappy. He said this is some sort of spooky action at a distance because in principle, in those days, they couldn't do the experiments. You might have a quantum object here correlated with another quantum object far away, and some measurement you do here would, if quantum physics is correct, if these laws are correct, instantaneously affect the object far away, maybe even on the other side of the universe. You couldn't control the result, so it's not a way to communicate, but this spooky action at a distance, Einstein said, this can't be right. This doesn't make sense. Similarly, the probabilistic nature of quantum theory, that you're not exactly calculating things, you're calculating essentially probabilities of what may happen. Einstein didn't like either. He said, does God really, by God he meant, is nature really described probabilistically? Does God, he thinks, does not play dice with the universe. It's not a random roll each time. However, as time went on and our technology improved, measurements were made which said, sorry, Einstein, quantum measurements and experiments have shown that this spooky action at a distance is real. This is a New York Times headline from 2015. And if you notice here, this is slightly more than a kilometer, 1,000-meter separation between two laboratories. This was in the Netherlands, in Delft, where solid chunks of diamond, this is actually a diamond lattice that has the carbon atoms in diamond, there were quantum spins inside of diamond which were correlated, and then a measurement was done on one, and they could find that the effect on the other one was essentially instantaneous, faster than the speed of light, and consistent with quantum theory. Amazing, isn't it? Amazing. So, sorry, Einstein. His musings and others and concerns seemed reasonable, but he was really grounded in a kind of human sense of what should be realistic rather than, ultimately, science-driven. What does the evidence show when you do the experiments, and what can we uncover about how the universe really works? These kinds of measurements, which are sometimes called Bell's inequalities, named after an Irish physicist named John Stuart Bell, to show that this spooky action at a distance is really real and really is how the universe works, was celebrated last fall in the Nobel Prize in Physics. These three men shared the Nobel Prize. This man was part of a group of people that did the very earliest Bell's inequality tests in the early 70s. This Frenchman here and his team improved them greatly as you got into the late 70s and the 80s. And this gentleman here, who's Austrian, took those sort of technology, physics results, and began exploiting them for interesting technologies. So you can say here, see the citation, for experiments with entangled photons, establishing the violation of Bell's inequalities, that's this spooky action at a distance, and pioneering quantum information science. Now, the rules of quantum mechanics, quantum physics, set down about 100 years ago, as I said. Still, over the last century, we've been demonstrating their veracity. But it didn't take long for applied physicists, engineers, and others to begin using the effects of quantum physics to develop useful technologies. So throughout the mid and late 20th century, there was sort of a quantum tech 1.0 boom, developing many different technologies that are based upon the laws of quantum physics. I just highlight a few here: lasers, atomic clocks used in the global positioning system, which we use for navigating and positioning ourselves. Your phones are generally in contact with GPS signals regularly to know where you are and what time it is, etc. Magnetic resonance imaging, which conventional MRI, for those of you who've had an MRI. How many people have had an MRI? Yeah, me too. Giant magnets that you're slid into. The reason they have a very large magnet is to make a very large magnetic field to try to polarize the nuclear spins in your body to give a big enough signal so they can do useful MRI. We're going to talk a little bit more about that later. Semiconductors, the properties of semiconductors, which are in computer chips inside your phone, your iPad, your laptop, mainframes, etc., are all based upon laws of quantum physics, and they continue to advance. The technology is not done. It continues to get better and better. But that 20th century advances were really using many particles, many electrons, many photons in a laser, et cetera, many spins in your body for magnetic imaging. Now, as we move in the 21st century, there's kind of a quantum tech 2.0 boom in which we're able to address and control individual particles, which are sometimes called qubits, which may give us capabilities like the ability to measure an image at the single atom level, maybe being able to do single protein structure inside of your bodies, non-invasively someday. To engineer and control matter at the single molecule level, communicate perfectly safely with entangled photons. That spooky action at a distance capability actually provides, if you do things correctly, with an ability to communicate. And if anybody interferes or tries to eavesdrop, you'll be able to know. They're essentially making a measurement which would collapse the wave function and perturb the thing you're doing, and you'd know, bing, somebody's listening. Or to compute exponentially faster on certain problems, not all problems, by exploiting superposition and entanglement in quantum computers. Now, I put question marks at the end of each of these because none of these things have really been realized fully yet. People are working on them. They may not work out, but people are industrious. Scientists and engineers are working hard to fully exploit the laws of quantum physics, not just kind of on average when we're dealing with many particles, but if we can do single particle addressing and control and really scale things up, it may lead to another set of very impactful technologies like the ones that began in the mid-20th century. There's a lot of effort on this new quantum tech 2.0 worldwide. Lots of money being put in, this is 2 years old here, by various governments around the world, not to mention all the big companies who are investing. So that's what's going on, but now I'm going to tell you a little bit. I'm going to now switch to these two stories that have come out of research that I've been involved with my collaborators and my students over the years. And I'm going to tell you about how quantum tools that we develop can help in terms of exploring aspects of the universe and also help life on Earth. And that sometimes the same tool you're developing to help answer questions about the universe can be reconfigured, re-engineered, or inspire a technology that can be very useful in everyday life, as I'm going to try to tell you. Really what we're doing is building bridges between the basic physics and the applications of the real world. That's what goes on. Scientists are trying to, at times, understand the universe, understand nature, and applied scientists and engineers are trying to develop technologies which will be useful. And they're not separate activities. All right, story number one, which goes all the way from the early 90s to today. And let's begin with a kind of special atomic clock that was being developed by myself and others, which we called the dual noble gas maser, a fancy name. I'll tell you what that means. And the explore the universe aspect of what we were doing with this technology was to answer a sort of question, is there some preferred direction to the universe? Or the laws of physics actually have a directionality to them? Not because you're near some star or planet, but if you're out in the middle of empty space, is every direction, the laws of physics, the same? Currently, we assume that's true. But there are some theories which say that does not have to be true, and so it's an experimental question. If there is some preferred direction to the universe, it would have some effect on matter, might change the mass of things like electrons slightly if you're aligned or anti-aligned with that direction. Might change the speed of light slightly, things like that. And we experimentally can search for it. So that's one of the goals of using this technology we developed, was to try to address that question. People had addressed it previously, but we thought we had the ability to do it with much better precision, much better sensitivity. It did work out. Spoiler alert, coming up in a few slides, we got an answer, and I'll tell you what that was. I won't tell you whether we found there is a preferred direction or not. Wait for that. So what does this dual noble gas maser mean? What's dual noble gas? What does that part mean? It means we were using two types of noble gases. Everybody heard of noble gases or inert gases? That column on the periodic table where they don't make molecules, like helium or helium-3, a particular isotope of helium. And the reason they don't make molecules, they're noble, like the nobles of old who are standoffish and wouldn't interact with the common people. I guess that's the origin of the name. And also xenon, a particular species of xenon. In both cases, these are chemically inert, meaning they don't make molecules. They're fairly common atoms, they just don't do anything, really, interestingly. But they have closed electron shells, which means that these electrons are tightly bound to their nuclei inside, and they don't want to form molecules. They just float around as gas, and that's it. Xenon is actually common in our Earth's atmosphere at a low concentration. Right? So you're breathing some of it right now at low concentration. Interestingly, these two isotopes, which are not radioactive, helium-3, xenon-129, have They have, in the case of helium, 3 nucleons, 2 protons and a neutron. And in the case of xenon, a total of 129 nucleons. And the various properties of those nucleons, the neutrons and protons, kind of balance off each other with just one extra N, one extra neutron left over in each nucleus. And with that comes a quantum property, quantized nuclear spin, which is an intrinsic angular momentum, and essentially associated with that is a magnetic moment. So they're like tiny little magnets. And you can, depending on whether they're oriented up or down, they're quantized to be either up or down aligned with a magnetic field. And if you make them flip, they will emit signals that you can detect, radio frequency, RF signals. The helium emits at a particularly higher frequency than the xenon, but they each radiate these signals, and we can detect them with little antennae. So that's what dual noble gas means. It's 2 types of noble gases. We're going to mix them together. They're going to emit their signals, and they're going to be at these different frequencies. The frequencies that they emit at are sensitive to the magnetic field we apply, but also potentially sensitive to this preferred direction of the universe question. Now, what is a maser? You might guess a maser is like a laser pointer. The L in laser is for light. The M in maser is for microwave or RF, same sort of thing, longer wavelength things. So a maser is in the microwave or RF region, kind of like a laser. That means it's longer wavelength oscillations of the electromagnetic field rather than very short oscillations in visible parts of the spectrum like a laser. So in the case of helium-3 and xenon-129, a maser is one in which, like with the laser, it's emitting continuous signals. The laser keeps emitting signals. The maser continues emitting signals. Out comes those RF signals from the helium-3 and the xenon-129. Now, during the 90s, we did a bunch of work with my collaborators to establish that these dual noble gas maser technology would work. And a key person involved with this is our own Tim Chupp here. You can see Tim's name. He was a key collaborator developing this technology. By about the year 2000, at my lab at the Center for Astrophysics, the Harvard-Smithsonian Center for Astrophysics, we built up inside of this metal tube here, those are magnetic shields, a bunch of electronics to measure things. We built up an operational dual noble gas maser, which was targeted at this preferred direction of the universe question. You can kind of think of it as laboratory cosmology. We're in a laboratory, but we're trying to answer questions about the universe, big questions. If you look inside the can, you would have found a chamber which had this double bulb structure, a so-called pump bulb and a maser bulb, made of glass, special kind of glass. The xenon and the helium is inside the glass. And if you zoom in, we can do quantum state preparation in the pump bulb, and then the gases will diffuse down into the maser bulb where they will emit their signals continuously. So that's this quantum state preparation up in this bulb, which is done, ironically a little bit with a laser. There's a laser which does the quantum state preparation in a little bit of a complicated process I won't go through here, but the xenon and the helium-3 have their quantum states prepared with the nuclear spins in one direction. They're gases, they diffuse down, and then they continuously emit their signals in this maser way. Then the gas diffuses back up to the pump bulb, gets reinitialized, and back. Now, there's gas everywhere, so some of the gas is down in the maser bulb, or some are in the pump bulb, so some are getting initialized and some are giving off the signal, and the whole thing just emits signals continuously in what could be seen as a kind of boring thing that's just putting out these 2 RF signals that you're detecting. And the way we operated it, they were kind of like high audio frequencies. So you hear one, another, if you wanted to, you could stick it on a speaker. We didn't. We recorded it with a data acquisition system, and we're just interested in the rate of oscillation, the frequencies of these oscillations. And I haven't really told you why do we use 2? Why this dual noble gas? Now I'll tell you. Because each are sensitive to magnetic fields, and we kind of control the magnetic fields as well as we can look at the difference between them to isolate any small remaining variations of things like magnetic field drift. Because we're really interested in this possible preferred direction of the universe thing, not mundane things like our electronics aren't perfect or there's tiny drifts in the temperature of the system or something like that. So basically making, this is common in precision measurements, a differential measurement You're measuring two things which are both sensitive to magnetic fields in a different way, but are both sensitive and could also be sensitive to the preferred direction of the universe. If you do the right kind of differential measurement, you can subtract out the mundane effects and just try to reveal the interesting things, like this preferred direction of the universe. Now, theories like string theory and some other ones which are attempting to deal with unifying quantum physics with general relativity and other questions said that it is, to this question of could there be a preferred direction, the answer is maybe. Not that there has to be, but maybe. A simple way of thinking about this is there could be some background field, indicated by the blue arrows, that we don't know about, might be there, that couples to normal matter. And that's what we're trying to see. We don't know if it exists. We don't know its direction. We don't know how strong it couples. But we do know that if it's there, and you're sitting on the Earth with a super precise instrument, and you change your direction relative to that field, you would see some tiny modulation in the laws of physics. So in particular, you'd find an orientation dependence of the maser signals as the Earth rotates and revolves around the sun. So yes, in fact, we had to monitor for days and weeks and months and years to be able to get sensitive enough and let the Earth do its thing to see whether there was any tiny effect. Is there any orientation dependent effect on these maser signals? And if there isn't, how well can we make the measurement? So, after several years, we concluded and got an answer. How many people think we found an effect? Raise your hand. Raise it high, be proud. How many people think we did not get an effect? Why do you think we did not get an effect? Maybe you would have heard about it or something like that? Well, you're right. We did not. How well did we do? We said there was no such thing to about 1 part in 10 to the 31. That means the maser signals do not change out to that. We're measuring the frequencies. And when I say the signals don't change, the frequencies are stable over this period of time to that, which means things like the mass of the atoms, the helium-3 and the xenon-129, are isotropic. They don't have an orientation dependence out to about, I think I got the right number of zeros, somebody could count. I was there doing that, making the PowerPoint slide, putting all those zeros in and going 28, 29, this sort of thing, out to so many digits. That means, at least to our degree of technology, the universe is very, very isotropic. The basic laws of physics do not affect things like this with orientation redependence. Maybe there is an effect out if you went another factor of 100 or 1,000 more sensitive, and there are other people subsequently, because this work was finished almost 20 years ago, who've made things better by about a factor of 100 more sensitive, and they continue not to see an effect. But this kind of pushing the state of the art of what we know, the things we think are true, but we are going to test them as well as we can and work hard, is actually quite useful. It drives our knowledge, so it's not just we're kind of sure, we're sure, and we know how sure we are. Out to 1 part in 10 to the 31, or now 10 to the 33 with other people's work subsequently. So, think about this. It's not something that that all of us should be doing, probably, or too much of the effort of humanity should be put into, but understanding our basic laws of physics as well as we can and pushing that state of the art is useful. And once in a while, when you do that, actually something new comes about. Things that were thought to be true, everybody was sure, turn out not to be, even in physics. Happens 2 or 3 times, 4 times a century. Not too often, but those are usually major step functions in our understanding. In the late 19th century, there was thought to be, absolutely had to be an ether, a background, kind of like this preferred direction thing I'm talking about, but not a directionality, some medium that was in empty space through which electromagnetic waves traveled. So many experiments, Michelson-Morley experiments, done to search for these sorts of things with great precision. They couldn't find it. This was a conundrum. Like us, they were not seeing an effect. Addressing that issue is one of the things that drove Einstein to develop the theory of relativity. And there are some other examples subsequently. So one of the reasons to do this is to know with precision and accuracy how well we really know our basic laws of physics. Tim mentioned that I got this Pipkin Award It was in 2005. That's me 20 years ago. So look, the younger version of me. Boyish kid there. So it says record sensitivities to violations of, this is the preferred direction stuff. Lorentz is a person's name and the Lorentz symmetry is this sort of reorientation symmetry, that sort of thing. But I also want to call out this. For innovative applications of masers, we've been talking about masers, to imaging. So now we're going to pivot. What does that mean, imaging? We're going to pivot from how this technology and the ideas for making these masers could be useful to life on Earth. Help life on Earth. I mentioned how these noble gases are chemically inert. That means they're safe for humans. You can actually inhale them. They don't harm you. You need to have some oxygen in there too, but if you mix it in instead of the nitrogen, the benign nitrogen we're breathing normally, no problem, in and out. And in fact, things like helium is often substituted for nitrogen in the air mixture that divers take who are going deep sea divers. It doesn't cause the bends. Nitrogen can be pressed into blood, at high pressure, causing bubbles in the blood. Helium does not. It's this inertness. It's actually safer in some ways. So in fact, because these noble gases, helium-3 and xenon-129, have nuclear spins, you can easily image them with MRI. And because you can do this quantum state preparation, you can do it at low magnetic field. You don't need the giant magnet of conventional MRI. So way back in the late 90s, this is our little home-built, there's wood box, hand-wound solenoid. We were making our own little mini MRI machines in parallel with doing that dual noble gas maser preferred direction of the universe experiment, because it was using a lot of the same ideas in architecture. We could just reprogram and do it in parallel. And we were able to make low field, about 100 times the Earth's magnetic field, images of the gases inside of little glass chambers that we blew to have, H for helium and triangles and other shapes. The applied magnetic field we were using with the solenoid was only about 1% of that that's used in a conventional hospital MRI where you'd go. So it could be much simpler and portable. Over the next few years, we built in our physics lab a walk-in human MRI machine. I don't know if we got approval for doing that, but we just did it. And this was a thing, this solenoids here, that's me, younger version of me. You could stand up and get imaged. You could lie down, you could sit, you could move around and do some dance moves, anything you wanted. It was easy to do because the magnetic fields were low. It wasn't that hard, and we were able to image things like the gases inhaled into human lungs, to do kind of quite high-resolution imaging of where the gas goes inside of human lungs and watch it go in and out. It's actually, this technology has been developed over the years into a diagnostic for cardiopulmonary function. That's great. But we were interested in doing more. We also wanted, in principle, to measure other parts of your body. Let's say the proton spins, not just these noble gases we're putting in, but the proton spins that exist within the water molecules, the fat molecules, all the tissue inside of your body, like in your brain, in a human head or brain. So we tried that too, and we knew we were at low magnetic field, and we didn't have a way to do quantum state preparation of the proton spins at this time. So we knew the signals will be low compared to those hospital MRIs, but we gave it a try. Yeah, that's the problem. No quantum state separation, no continuous RF signals means that the magnitude of the signal we're getting out from the protons in the body at that time weren't very strong, and so maybe it's not so surprising we got not very good blobby images. That's like the kind of image you'd get of your head. It looks like E.T. or something like that, right? Or a space alien. That's not going to be very useful. We could kind of do a crude image, and it wouldn't have surprised anyone. You're at low magnetic field, dude. It's not going to work. You don't have this state selection. You don't have these noble gases. It's not going to work. In about 2010, 2011, however, we built a next generation system. It was relocated to Massachusetts General Hospital. The PI of that lab was Matt Rosen, who'd previously been a postdoc working with me, and was actually a University of Michigan PhD, one of Tim Chupp's students who got his degree in 2001. And at that time, there was this idea to make the MRI, to be able to do things like brain imaging, work like a maser. Not be a maser. We don't have the way to do the quantum state preparation. But there were techniques to be able to make the signals much larger by driving with coherent driving of the nuclear spins, the proton spins, to give much larger signals, have efficient RF signals, really using an idea similar to what happens in a maser naturally. And with that technique, Pretty good brain images. Not fantastic yet, but pretty good were able to be formed at low field in this walk-in system. It was time to commercialize. And that's what happened. A company was formed called Hyperfine in 2014. It's operational to today. And they developed with, I'm a co-founder, but I was not really involved in this sort of work. Wonderful engineers inside of the company developed a portable, low-cost MRI device, which they call Swoop. And it costs about 20 times less than a conventional high-field MRI machine. It, again, works at very low magnetic field, so therefore it can operate anywhere and with any kind of person. Implants, you can have your phone with you, et cetera. At low magnetic field, no problem. You can take it, it's on wheels. You can take it to the patient, in the emergency rooms, in the intensive care units, outside of the hospital. It's FDA cleared. It has Gates Foundation support for going into the developing world, as I'll mention to you. And it works as well. But a key thing was this ability to use these get these maser-like measurement sequences which could boost the signal and be able to make high-quality images at low field. As one example, in 2020, the swoops were used in intensive care units to help COVID patients in the ICU. Here's an example of a swoop MRI in the hospital room for an unfortunately very sick person, monitoring them continuously. As you may know, one of the things that could happen when people are very ill with COVID and intubated is there can be brain damage over time. And you don't know this is going on. They're often in a coma, they're often unconscious, you don't have a way to check them, and they're very ill. There's electronics keeping them alive. You can't take them to a regular MRI machine. The electronics is incompatible with it. They're also very contagious. So instead, you bring the MRI machine to them and you can have it operating continuously. It's compatible with the electronics keeping them alive, and you can monitor what's going on inside of their brains, et cetera, and get high-quality images. This is from a published paper. Unfortunately, they did find in certain cases, some of these people who'd been there for an extended period of time had serious brain damage that occurred because of COVID, but they were able to quantify that and help some of them. There are now hundreds of these swoops being delivered and used. Hyperfine went public in late 2021. They can be used in hospital room settings. They can roll around in and out of emergency wards. They can operate off of batteries. They don't need special shielding or special power. They can just plug into the wall or use a battery. They're now being delivered to resource-challenged places around the world. That's what the Gates Foundation is funding. So, for example, in Uganda and Malawi, there are some rural villages where they have no significant healthcare equipment. No, there might be 2 MRI machines in the entire country. There's no way to be able to get these kind of imaging tools to people or the people to the imaging tools unless you have something that can operate anywhere and is low cost and doesn't need an expert to run it. So in the case of these things, they were sent in a crate. Nobody from the company came, right? They were just on Zoom instructing the local people how to use it, and within 2 hours they were scanning people off of an iPad because it's so easy to use, because it could help looking at children, whether they are having hydrocephalus or other kinds of problems due to common diseases like malaria there. In late February in Science magazine, there was an article about this story about Hyperfine called MRI for All, which was published, which tells a little bit of the tale, and it also talks to many of the clinicians, the doctors who are starting to use it, about how they're trying to figure out the use cases. The images are much higher quality than the early stage work, but still not as high quality as you get in a state-of-the-art several Tesla system in a hospital. So one of the key questions to answer is good but not great images, somewhat degraded images, at much lower cost where you can do it anywhere. What's the trade-offs? What's the cost benefit? Where's the right places to use them, and how does it all work out? As it says, portable low-field scanners could revolutionize medical imaging in nations rich and poor if doctors embrace them. So that's the thing, figuring out the right way to have them be used. That was story 1. Now story 2, where there'll be some demos and diamonds. Diamonds have defects in them. This nice little set of balls coupled to each other is have these black balls in the diamond lattice configuration of the carbon atoms that make up diamond. As you might know, diamond is a particular arrangement of carbon atoms in a solid form. They have 4 crystalline axes. There's one, another, another, and another. And there's symmetry throughout a perfect diamond. If you want to hand this around, if people would like to look at it, just give it back at the end. That's every black ball there would be a carbon atom in a perfect diamond lattice. But almost no diamonds are perfect, or pure. They typically will have some kinds of defects. A missing carbon atom that's not there for some reason, called a vacancy. Perhaps that missing atom is replaced by another atom that's nearby on the periodic table, like nitrogen or boron. Or a cluster of these vacancies, or a dislocation where one layer in the lattice is offset from the other. Whatever way the diamond was grown, whether naturally occurred underground or was synthetically grown in the laboratories, which most of the diamonds are today that are used in scientific applications and industrial applications, you may try to make it perfect, and you may get it reasonably perfect, but they'll typically have defects. And these defects are the source of things like color in diamonds and in other gems, like rubies and sapphires. Without the defects, that's when you get the perfect crystal clear or near perfect crystal clear diamonds. These have less defects, I'm sure there's some, and these have more. The defects, it turns out, can have quantum properties. Because what happens is, let's say you have a couple carbon atoms in a lattice missing. One's replaced by a nitrogen, one's a vacancy. That means right around that defect, things are perturbed and the electrons are kind of trapped there. And they are a little like an atom now held in this matrix of the carbon atoms making up the diamond lattice. Again, this shows you the lattice of carbon atoms and a particularly common type of defect which gives pinkish reddish color to diamonds, known as the nitrogen vacancy color center. So one carbon atom replaced by a nitrogen, and one is a vacancy, a missing carbon atom. This occurs sometimes in naturally occurring diamonds. Nitrogen's common in our environment. During the diamond formation, a little bit can get in there, as well as other species. And it happens to some degree in the diamonds that are made in laboratories. But you can also introduce these NVs and other defects when they're made in laboratories or made industrially purposely. And it turns they have useful properties, as I'm going to tell you, the defects, not just giving things color. Oops, excuse me. So again, this NV, this nitrogen vacancy color center, it makes diamonds pink. So that's this region here. And some of the interesting quantum properties of the electrons, which are associated with this defect, is that they can emit and absorb photons, particles of light, one at a time. So if you illuminate the NV with green light, it will emit red photons, one at a time. It doesn't emit 1.5 photons, but one at a time, boom, at a certain rate, like this. Keep illuminating with green, it'll keep emitting red photons. That's kind of interesting. It also has quantum properties like quantized electron spin. The electrons which are trapped around the nitrogen in the vacancy have angular momentum and spin. Kind of like those helium-3 and xenon-129 atoms had spin inside their nuclei, but now it's not the nucleus, it's the electrons. And the magnetic moment that's associated with electrons, typically, and their spin is like 1,000 times larger than that with nuclear spins. You can have them quantized up or down. So that's an atomic scale magnet, really, that can act like a small magnet that itself can be very sensitive to magnetic fields. And interestingly, if you illuminate with green light, if the spin is in this direction, essentially the magnet, the north is up, it emits at a fast rate, the red photons, whereas if you're in the other direction, it emits at a slower rate. We can understand, physicists have figured out the quantum physics as to why the rates of photon emission are different. But it's key because now you can tell which way the magnet is pointing, which way the spin is pointing. Are you getting a high rate of photons out or a low rate? Right? So that gives you a measurable. We now know which way it's pointing through the rate of red photons it's emitting. It gives an optical method to detect the spin orientation. And it means since the size of this little atomic scale magnet is large, that means it's sensitive to magnetic fields. These properties make it a very good atomic scale magnetometer, meaning a device to measure magnetic fields. The orientation of that little magnet, it's a strong magnet, an external field, a weak field, can reorient it, and you can determine what's happened with the rate of the red photons that come out, as long as you're illuminating it with green light. So if you do things in this controlled way, you have this remarkably sensitive quantum device that's atomic scale and can be used for many things. I'll give you a little summary of some of the things it's been used for, this NV Center in Diamond, over the last 15 years or so. But first I want to show you some of the faces of the people who did some of the key demonstration work. So the first demos that these defects can be used as sensors, quantum diamond sensors, was done at Harvard back when I was a PI there in 2008 by a collaboration of 3 research groups, myself, my colleagues Misha Lukin and Amir Yacobi. But as usual at universities, as you know, the professors may have some good idea, and they may direct the research and get involved a little bit in helping out, but the people who do the vast majority of the work, the creative work, the hard work, are the students and the postdocs. That's part of their training and part of how academic research works. And this is the group of people who were involved in the first work, the very first paper, and then they were at this point working on the second publication that would come out in 2009, et cetera. It's a collaboration of them, and we got them together. I love this photo. It's great. I'm glad they took it. One fellow was missing that day, and so I've just stuck his picture in there in the corner. At the end of the talk, I'll tell you where are they now. What are they doing? But over the 15 years since those first demos in the lab by the students and the postdocs, these quantum diamond sensors have evolved to being useful for a wide range of applications, just a few of which I show here. They're very good at doing high spatial resolution imaging of magnetic fields that come from special materials and probing things in condensed matter physics, like how electrons flow in graphene like a fluid down a pipe, having viscosity and hydrodynamically, very different from how electrons flow in something like copper or gold, a regular conductor, or cool-looking structures, this is known as a skyrmion in magnetic multilayers. You can use them in biological systems. Diamond is a robust material. You can put it in direct contact with living things, and there's no problem. And these atomic scale defects, you can have one or many of them, can sense what's going on inside of living creatures. So this is the magnetic field pattern that comes from a micron scale bacterium known as a magnetotactic bacterium. I put the black line is just where the bacteria was, and the blue and the red are the magnetic fields that you get. These bacteria, they're prokaryotes, meaning they're single-celled organisms without a cell nucleus. They evolved, it's believed, more than 2 billion years ago. They evolved to synthesize a chain of magnetic nanoparticles tethered with proteins and tethered to their bodies, line up the domains, the magnetic domains of those magnetic nanoparticles. They do this naturally, inside their bodies like a little compass needle, and then they use this, the forces that external fields put on them, to navigate themselves in the Earth's magnetic field. They're anaerobes, and they like to be down in areas of ponds and water low where the oxygen levels are low. And if you take some and you put them in the southern hemisphere, in a couple generations, they've switched the orientation of the magnetic moment somehow, we don't know, and now can navigate appropriately in the opposite sign magnetic field. These things evolved 2 billion years ago, and they evolved naturally occurring magnetic compasses inside of them. And what genes are used to do this work, some of those same genes are found in us. Probably not to synthesize little magnetic nanoparticles inside of us, but probably used in ways to regulate iron. And so there's a whole field of biology that wants to understand these creatures and the genetic mechanisms that lead to this remarkable behavior. And one of the things they need to do is see how the magnetic behavior is manifested, and they'd like a magnetic microscope to monitor these creatures, together with all the other tools they use. And these quantum diamond sensors make a magnetic microscope, which they can use, and they do these days, to take pictures of this. In a very different application, you can use these diamond sensors, and people are doing this now. Companies are developing this but somewhat similar to what the bacteria do a couple billion years later, to navigate by the Earth's magnetic field, small variations in the Earth's magnetic field. For example, when GPS, you don't have access to GPS. You're deep underwater, deep underground. GPS has gone out for some reason, et cetera. So there's a lot of work on magnetic-based navigation and the diamond sensors, because someone's got the crystal lattice around here that I handed around. wherever it is, floating around. As you'll see, it's got these 4 axes, and their NVs can be along all the axes, which means any projection of the magnetic field vector, or any magnetic field vector will have different projections along the axes, and you can read this out easily in a way that gives you not just a sensor of the magnetic fields, but its direction too. And then they're so sensitive that you can do things like take animals. This is a whole marine worm here, and it can have an action potential in its neuron that it uses just to withdraw itself when it thinks a predator is nearby, and you can measure that pulse outside the animal non-invasively. So these are some sense across the life and physical sciences of some of the utility of these diamond sensors. They're very sensitive, they have high spatial resolution, they have this vector sensing capability, and they work pretty easily. They're sort of simple systems to make work. There's also many modalities. You can have bulk diamond chips grown in a lab that have many of these NVs inside of them. So there's a very large high density. That's why it looks purpley pink. You can have a diamond chip that just has the NVs at the surface. Let's say you want to make that magnetic microscope for the bacteria. You want to get a high spatial resolution, so you just have the NVs at the surface and you image it onto a camera. You can make nanodiamonds that can go into living creatures and monitor things like the magnetic fields or the temperature inside of them with maybe 1 NV inside of each nanodiamond. You can have an individual NV, 5 microns here, scanned over a surface of interest a few nanometers away to make these remarkable maps of magnetic fields and things like the skyrmions I showed, et cetera. So many different modalities, and over the last 15 years, the technology has proliferated. But now I'll give you I've said several applications, but 2 particular ones. One that's relevant to exploring the universe, and the other about helping life on Earth. So this is one I love because it was so unexpected for me and has such impact in really neat areas of science. It influences or informs our understanding of the origin of the solar system and life on Earth. There is good understanding that magnetic fields shapes the formations of solar systems, and our solar system in particular. This cartoon indicates, in the case of our solar system, the very early sun. Gravitational instability, maybe a couple million years after the sun begins to form and undergo early stages of nuclear fusion. Planets have not yet formed. There's a giant swirling plasma dust disk around that early sun. That means it's electrically charged. Electrical currents are flowing in it, creating magnetic fields, significant magnetic fields. Those magnetic fields, we'd like to know what their strengths were. What were these fields? As a function of time and position and magnitude away from the early sun, it's thought to have influenced the formation of the planets, where the planets formed. Similarly, what was the Earth's magnetic field in the very early days? When did the geodynamo get formed? And what was its magnitude as a function of time? As you might know, the Earth's magnetic field screens the Earth greatly from cosmic rays and particles from outer space, making the surface of the Earth much more habitable, much more relevant and enabling to life prospering. So when did the geodynamo begin, and what's its history? To answer those questions, it turns out Earth and planetary sciences, like my colleague Roger Fu from Harvard, go out into the field and find very old rocks. Roger's a kind of Indiana Jones type character. Here he is, high on the cliff of a rock cliff in Western Australia in the desert, where they've been able to determine that there's bits and pieces inside of these old rocks that can be more than 4 billion years old. They want to examine these bits and pieces to try to determine, are there records inside of iron-bearing grains that have retained the magnetization in them retains information about the magnetic fields in the early Earth. And then Roger brings these kinds of rocks back, slices them up, and uses them in he calls the quantum diamond microscope, be able to make images of the tiny magnetic grains inside using these NVs in diamond. Inside of which is one of these imager-based diamonds with the NVs just at the surface layer. Now, it's key to not perturb the sample. This is true for those biosamples I talked about, but the rocks too. You don't want to have the green light that you're using to energize the NVs get into the sample and heat it up or something like that. Yet you need the green light to cause the red photons to come out. So fortunately, there's a way to do that, and now it's, I think, time for the first demo, which will be about total internal reflection. Let's see, they're going to switch over. Yeah. Won't change? Can I go? Okay, right. So I was told always to wait for the demo people. So this is a big block of a plasticky kind of material. It has an index of refraction which is larger than that of air. You know, a laser pointer passing through air. Air has a very small index of refraction, slightly greater than 1. This is much bigger than 1. Diamond, the material through which we want to send green light, kind of like this green laser pointer to induce the red photons to come out, has an even larger index of refraction. Fortunately, that means if you illuminate, and you can see in that photo, that's an actual photo of the green light coming from the side through the diamond, you can excite the NVs without the green light significantly perturbing the sample by using an effect known as total internal reflection. Do you see how the green light is bouncing off the top and then coming out and on the table? But it's not coming in. If this was the diamond surface with the NVs, and I want to excite these NVs with green light, and I have my delicate sample on top, I don't want the green light going into it. It's not. There's no green light going here. It bounces off the surface and comes through. And this bouncing is due to conservation of momentum considerations that you have to take into account the differences in the index of refraction of the medium, plastic here, diamond there, and the surrounding medium, air. In both cases, air, air. That's related to also to, if you look at refraction, if you look at the angle of the laser pointer here, and you can see hopefully the laser beam passing through the medium, you can see that they're not lined up. This comes at this angle, and then the green light is going at a different angle. That's related to Snell's law that has to do with the angle of incidence to the angle of refraction, and you can see the light incident passing through at different angles. Why? Conservation of momentum, linear momentum that the photons carry, given that you're moving in this medium of different index of refraction, and the momenta is different in the two cases. Okay, so basic physics that you might learn in a first or second year course in college ends up being, in a technological way, very important for being able to make a technology like this work. What can they learn? Well, here's a cool thing. Here's a meteorite, the Allende meteorite. It fell in Mexico in 1969, so not that long ago in historic times, obviously. It's about this big, what eventually got to Earth. It started as a bigger thing, goes through the Earth's atmosphere, heats up on the outside. The outer parts get very hot, but turns out the time it takes to fall through and the thermal conductivity of the object is such that in the core, inside here, it stayed cold, coming from outer space. And by doing analysis of the chemical makeup and the isotopic concentrations and distributions inside this meteorite, scientists were able to determine that it had broken off from an asteroid and had been an asteroid that was made up of material that was primordial, meaning existed before the planets formed and has been flying around in outer space in our solar system for a long time, billions of years, literally. Now, there probably are collisions now and then over that long period of time. So you've got to do studies of the meteorite to make sure that it has never been heated up, not just falling through the atmosphere, but during 2 billion years ago or at some random time in some big collision that wouldn't have heated the whole thing up if you want to use magnetic imaging of the rocks inside to try to learn about the magnetic field in the very early solar system before the planets existed. So that's a key thing to do, is to do that kind of analysis. And part of what you can do is look at the chemical composition. If you heat things up high enough to reset magnetic fields in certain high Curie point materials, then you will not have certain other chemical substances survive. They'd degrade or undergo some reaction. Similarly, if you had ever heated things up, let's say due to a collision, to the point where all the magnetization in the grains were reset, they would probably be all aligned rather than randomly oriented if they'd all come together originally. So there's certain criteria that the results have to pass to be able to conclude that what you're learning really tells you about the magnetic fields in the super early solar system. They gently cut the rock up and can find these grains inside that have high Curie points associated with them, which means you have to heat them very high to be able to reset the magnetization. That's an optical image. Then they zoom into areas that seem interesting to them. See the spatial length scales? This whole thing's about 1 millimeter. This is a fraction of a millimeter across. They're zooming in with an optical microscope. And then you use the QDM to make a magnetic image that can tell you things about what the magnetic fields were in the early solar system, assuming the magnetization has never been reset. The conclusions from this meteorite and others that have been analyzed is that the ancient magnetic fields in the solar system, say at Earth's radius, Mars's, etc., were on the order of 100,000 times larger than the magnetic fields in the solar system today, and consistent with theoretical models and what's observed in other forming solar systems about that swirling plasma dust disk, the large electrical currents, the large magnetic fields, and instabilities driven by the magnetic fields affecting back onto the charged particles, causing shock waves in the dust disk that then induced and helped to induce planet formation. So they've been able to learn these sorts of things. What was the magnetic field 2 million years after the sun formed? 3 million, 4 million, at 1 astronomical unit, 2, 3, etc. They're building up this kind of database. So we, by looking at the time machines that are inside of these recorders and these rocks inside these meteorites, learn about the formation of the planets in our solar system. Okay, another demo. I mentioned Curie point more than once there. That's named after Curie, Pierre and Marie Curie. It's one of the many things that they discovered or did research on. Materials which are magnetic, solid materials, if you heat them up enough, the magnetic moments inside, those electron spins which are aligned in a magnet, they'll get enough thermal energy and they'll start not being aligned and they'll lose the magnetic properties. Then when they cool back down, they'll gain their magnetic properties again. So if one of those rocks or meteorites was magnetized in an early solar system, but 1 billion years later there was a huge collision, the whole thing got hot, above its Curie point, reset the magnetizations, and then magnetized again, you wouldn't be learning about the magnetization in the very early solar system. You'd be learning about some event that you don't know when it happened in the middle, 4.5 billion years between then and now. So it's important to understand and look at grains inside of rocks that have properties that have extremely high Curie points, so that this resetting, this heating, any heating that happened was not up to the Curie point and would not have reset the magnetization. That's one of the many criteria they look at. So this demo is going to be about showing you a Curie point in a material that is not like what was in these rocks. It has a much lower Curie temperature, so with a nice little Bunsen burner thing, we can reset the magnetization. So this is a magnet, and this piece here is a magnetized material, a bronze, that has a relatively low Curie point. When I begin heating it, which I'm going to do soon, it will warm up, and at some point, it'll have enough thermal energy that the magnetic moments will start being randomized. It will lose its magnetic properties, and instead of being attached, you'll watch it swing away. No longer a magnet anymore. Then it'll cool down, regain a magnetization, and then the magnet will attract it again. And then we can repeat this delightful process. It's warming. It's exciting. Hey, there we go. Okay? It's cooling now. Oh. Let's do it again. It probably hasn't cooled up. So it didn't take as long because it hadn't. Doesn't take it long. We're getting it just above the Curie point. Not a magnet anymore, and cools a little bit magnet. This kind of thing, right? So that's what, okay, one more time. There we go. Yeah. So, what do I do again? I put this on here. They told me what to do. There we go. So there's a cool little, or a warm little demo on Curie points. To get to the point, and we'll switch back, please. To get to the point where the Earth and planetary scientists can reliably make these grandiose conclusions about the early solar system, they have to I've emphasized this, I'll say it again. They have to know the materials. They have to look at the chemical composition, understand the isotopic ratios, which tell you about radioactive decay and the age. A lot of things have to be done, but the magnetic mapping to learn what the magnetic fields were or are in these rocks and meteorites is essential. And one of the key things that this quantum diamond microscope provides is this combo of features. It has high spatial resolution. You can look across the entire field of view. It has good sensitivity and has this vector capability. The other technologies they had before this quantum diamond microscope did not have this combo of features, and you can have minimal perturbation on the sample, keeping the light out. It's a room temperature thing, as opposed to other technologies for sensitive magnetic mapping, which might be cryogenic, and then you're altering the properties of the rocks by taking them down to low temperatures, et cetera. So it's this combo properties, the quantum properties of the NVs together with other properties that make it very useful. It's now become a widely adopted tool in the community. This is at the Institute for Rock Magnetism at the University of Minnesota, and now these quantum diamond microscopes. You can see they're not that fancy. They're just basketball-sized objects. They have the diamond in them and the green laser and a camera to measure the red photons. These cool-looking coils are just to be able to apply different strengths of magnetic fields to the system. And here's a student and a postdoc, for example, using the quantum diamond microscopes that they have, and many other labs now have them in this field. So this is an example of over the last 15 years, you discover a phenomenon that exists, these defects in diamond, people work and develop it, figure out some things that it's useful for, develop some technology, and it translates into another field, which can tell us a little bit about as our exploration of our planet and our solar system and the universe. The same technology, though, can be redeployed as a medical diagnostic tool to be able to do single cell or single biomarker detection and help life on Earth. So let's say you had a blood sample or some other biosample. Let's take a blood sample. Here it is on a microscope slide, and you do an optical image. Turns out there's one tumor cell that's been placed inside of that blood sample. Can you tell where it is? The answer, no, you can't see. All you see is some black mottled stuff. Even if you fluorescently labeled the tumor cell, it would be difficult to see inside of a thick sample of blood. If, however, you can selectively label with magnetic nanoparticles the tumor cell, because you know the properties of the tumor cell, and this can be done, then you can, and because magnetic fields pass through things like blood or tissue unperturbed, you can use the quantum diamond microscope to do a magnetic image and see where the cell is. And then you know, here it is. It was here. We just couldn't see it with the other technology. So single cell detection capability, single biomarker detection capability is quite easy. And if there are many of them, let's say circulating tumor cells that are in the sample, each one of these is a signature. You can take an image quickly, and a computer can quickly analyze this and count exactly how many there are. You want to find all bad cells. So in fact, a company, QDTI, founder of this company, although I'm an advisor to them, I don't really work in them, which has boxed up this quantum diamond microscope technology, taken this basic ability to be able to sense these biomarkers. They're now in hospitals being tested. Looks like it'll be more sensitive. It's small, it's like the size of a microwave oven, something like that. Relatively simple, as I was emphasizing for the rock setup. It's not a very complicated device. That's good. That means it's not that expensive to manufacture. That means it's pretty robust and easy to use. So that's a help the life on Earth version. The same technology based upon these quantum defects in diamond can do many things. And some of it's about basic science, and some of it's about helping life on Earth. Okay, I'm coming to the end now. I wanted to tell you, where are they now? Remember this photo of the folks in 2008 in the lab, late 2008? So what are they doing now? This shows you what they are all up to. Paolo Capillaro here is a professor at MIT, as is Paul Stamwicks. That's Liang Zhang and Peter Maurer, who are both professors at the University of Chicago. Lynn Pham works at MIT Lincoln Lab. Jake Taylor here was the lead at the White House for quantum science and technology, the lead advisor at the White House, and then left a year or so ago into quantum industry, and many others. Geronimo Mays here, who was the first author on the first paper. He came from Chile originally, got his PhD at Harvard, and now is a professor back in Chile. So some are involved in industry, some in government. Many still work in the quantum field. And I mean, that's one of the, that's what universities primarily do. We educate people and do basic research through training young people in science and technology. And these are the sorts of people, as well as many at Michigan and other schools, who deserve a lot of credit for getting things done. My one message was that everything is quantum, and that we want to work on building bridges to basic science questions to explore the universe and also help life on Earth. I thank you for your attention. I'm happy to answer questions like, aren't diamonds expensive? We can talk about that. I'm supposed to, the University of Maryland manages my conflicts of interest, so I'm supposed to put this up here so that you can read and enjoy. That's their language. And thank you very much for your attention. How'd we do on time, Tim?
Oh, that's great, Ron. Okay. Thank you so much for that brilliant exposition, I think, and tour. We do have some questions that came in from our listeners, that even though I did not write up, and our viewers, even though I didn't write the email address physics@umich.edu. So you still have a chance. I can get them on my phone. If you do send the questions in, and then we'll also take questions from the audience. So you had several parts to your presentation. I want to thank you for the shout out. I didn't really deserve that, but
yes,
thanks
you did.
Anyway.
Yes, you did. Yes, you were a major contributor, as were your students, so that's wonderful.
Okay, so let's start here with entanglement, I guess. So the question is, how far apart do you have to have detectors to say that photons are entangled, practically? Does it really have to be kilometers?
No, it does not have to be kilometers, and entanglement is at work in all sorts of physics experiments all the time. In fact, atomic clocks are typically operating on what's known as clock transitions, which are magnetic field insensitive hyperfine transitions typically, or insensitive to leading order, that typically involve, I'm going to use physics lingo here, and MF equals 0 states, which means there's an electronic spin in the atom and a nuclear spin, and you're in some coherent superposition of, let's say, electronic spin up and down, either plus or minus the other. And that plus or minus means you have an entangled state of nuclear and electronic spins. So there's entanglement throughout quantum physics and technologies. However, the question is really getting at these Bell's inequality tests, and to really show that that the canonical interpretation of quantum mechanics is correct, and you can't have some sort of hidden variable theory that would explain things as well. You have to satisfy certain criteria, including things like being outside of the light cone, which is, I think, what this questioner is asking about. What does a light cone mean? That means there's signaling possible, as we know, at the speed of light. So if you wanted to cheat in one of these Bell's inequality tests, or if nature wanted to cheat, if you made a measurement here, and the time it took you to check over here that you were getting a correlation was less than the time it took light to send a signal over, then in some sense a cheater, or nature cheating, could send the signal, hey, we got spin up over here, which means it's got to be spin down over there. Set the experiment to give you spin down. And they're so slow to do the experiment that the signal could arrive and send information. So one of the challenges throughout doing these Bell's inequality experiments and improving them, from the first ones by Clauser and Friedman and others through Aspect, and to today, the one in Delft was led by a man named Ronald Hansen and his team, is to close these loopholes and be able to make everything work super fast and super efficient so that you can operate outside of the light cone. Now, the specific question is, how close could you make things get? And that gets more challenging, right? Because the time, in some sense, sending things a long distance is hard because you have to be able to coordinate, and there's practical challenges. But very close is challenging too, because now the time it takes light to go from here to there is very short. So I don't remember the shortest distance, off the top of my head, the shortest distance in which a Bell's inequality test that satisfies all the loopholes has been performed. I'd have to check on that. But there's certainly things which are done at the kind of benchtop scale. It's been actually more interesting to physicists, I think, to probe how far away you can get, not because it's technically easier, but they want to answer questions like, not just at a kilometer, but when we get to 100 kilometers and a light year, et cetera, does this this picture of quantum entanglement persist, and is it correct to arbitrarily large length scales? I think that's really where some of the frontier challenges are. Okay, and questions?
Okay, actually, are there any audience questions about quantum entanglement and the very first part? Okay.
Two there. Yeah, sorry.
Yeah, early in the presentation with the maser, you talked about concluding that the universe was isotropic.
Yep.
No directionality.
That we could find in our particular experiment.
Right, and so I was just hit me that, wait, you're saying the universe from an experiment based on planet Earth, is it not certainly possible that elsewhere, like in the vicinity of a black hole or something, there could be directionality?
Absolutely. So we only are doing our experiment in our context of doing it on Earth as it moves around the sun. So let's call it a fraction of our solar system we were probing. And we were doing it in the context, in one sense, of unbiased by theory. There are theories which motivate this, but we don't need to also have that motivation. We just want to do what we can do as well as we can. But to speak about the theoretical motivation a little bit, I mentioned string theory. There are a variety of so-called beyond standard model ideas, as well as certain cosmology theories, which would say that if those motivations are correct, their qualitative picture is that in the early universe, after the Big Bang, there could have been some additional fields, vector or tensor fields, which froze out, randomly oriented, and then the universe undergoes, we believe, an inflationary expansion, which makes things very homogeneous. So therefore, if that view is correct, a measurement made at almost any place would be probing this background field, which would in principle be the same everywhere. But absolutely, people can concoct and have proposals in which there is heterogeneity, spatial heterogeneity in here versus over there versus a black hole versus 10 billion light years away, or the early universe might be somewhat different. In particular, one of those, to give you one example, and it's not spatial, but it's temporal heterogeneity. One form of the background field comes from something which is called quintessence, which is a field which evolves temporally as the universe undergoes inflationary expansion. In that case, the magnitude of the field, and hence the effect on matter, like masses of atoms, et cetera, would be very different in the very early universe versus now, 13-something billion years later. Right? No one experiment is going to, each experiment is just what it is. We can't overinterpret it, but for that experiment done in the way that we did it, we saw no orientation dependence. Just for the people in the audience who are physicists know a little bit more, there was another part to the experiment we did in which we were also probing for not just an orientation dependence, but a boost dependence, because the Lorentz symmetry involves reorientations as well as changes in frame and velocity, essentially, and we also found no boost dependence.
Another question?
Then we can talk about diamonds.
No, back to entanglement.
Yeah.
Can I know that two particles are entangled without a measurement? And if that's the case, is there a measurement that I can do that will only cause one state to collapse? In other words, it's a measurement that only measures up and doesn't count as a measurement if it's down.
There are, if you have an,
Get away from the statistical.
yeah. If you have a state which is a coherent superposition of other states, conditions, and it's also entangled with another state, a measurement, you have to look at what aspects of that overall system would be affected. And so if you are then doing a projection on one aspect of the system, you will be picking out of whatever coherent superposition you have for that aspect of the system, you'll be in one run of the experiment, probabilistically, you'll be getting one answer for that component of things, which may affect the rest of your entangled system or may minimally affect it, depending upon how you've set things up. So, as an example, this segues actually over into diamond. Something I did not talk about here, I talked a little bit about yesterday when I gave a physics seminar, is that some of the measurements protocols that we use when we're reading out these NV centers in Diamond, we take advantage of the fact that each individual NV center has an electronic spin. I talked about that here as if it's a little bar magnet. But it also has a nuclear spin. The nitrogen atom has a nuclear spin. There's a hyperfine interaction between the two. And so if you wanted to do a complete description of the NV, it would include both the electronic and the nuclear spin, not just the electronic spin that I was talking about here. For many of the measurements done to date, people kind of ignore the nuclear spin, but you can actually use it as a resource by making an entangled state of the electronic spin and the nuclear spin inside the NV, so not physically separated. It's a little bit like one of those clock states I was saying. And because the electronic spin is very sensitive to the environment and the nuclear spin is largely insensitive, much less sensitive, the magnetic moment it has is about 1,000 times smaller, so it's much less sensitive. The measurement that you do with the NV to sense external fields is primarily perturbing the electronic spin. You can map that information into the nuclear spin by making an entangled state of the electronic and nuclear spin. And then when you read out the information, the optical transition that gives you the red photons when you turn the green light on, that does not affect the nuclear spin. That does make a projection and a measurement on the electronic spin. So you get it, sorry, but you've lost your information on the electronic spin and you get out a photon, either the fast rate of photon emission or the low rate. But, importantly, some of the information remains and is not reset in the nuclear spin, so then you can re-entangle the nuclear spin with the electronic spin and read out again, and then re-entangle and read out, and re-entangle and read out. So for one measurement, instead of just one readout, you can do one measurement and get many readouts. That means you can boost your signal to noise, essentially like an amplifier, because you're putting the, it's not an amplifier in the sense of downstream boosting the signal. It's allowing you to read out many times. So that's what's called a quantum non-demolition measurement, because, or a better name might be quantum partial demolition measurement. You are projecting or collapsing part of the wave function, but not all of it because of the nature of the measurement. And if you're smart about what you do and can take advantage, and you have the tools to be able to take advantage of how you move information between different parts of the wave function, or Hilbert space, if you want to talk about it that way, one can at times get benefit from that technologically. Right? So it's not getting away from this totally from the statistical nature, but it is to some degree taking advantage of the different types of qubits and their different properties, and the fact that not every measurement completely collapses all aspects of the wave function. Because the measurement we do with the green light on and the red light out affects the electronic spin only, not the nuclear spin. So even though it's entangled with the nuclear spin, it's only the electronic part that's reset.
Okay, we're going to get to other parts of your presentation, but I just wanted to finish maybe with a brief answer to this first part about a preferred direction. And you said that string theory could provide or allow or even predict a preferred direction. So since you haven't seen one, here's the, and I quote, "Is string theory bogus?"
No comment. No opinion. I don't have an informed enough opinion. I don't understand string theory well enough myself to be able to comment intelligently on it. I'm an experimentalist, a so-called low-energy experimentalist, which doesn't mean I have low energy like this. It means we use tools, small lab-scale tools, and build them and that kind of thing, rather than giant particle accelerators, et cetera. So as an experimentalist, my own work and the work of colleagues whose work I understand has to date shown no evidence that I can see for string theory. The actual theoretical underpinnings by those brilliant people who construct it may have merit as mathematically or theoretically, but I can't comment upon it beyond that. Trying to be very politically correct and also accurate in a way.
Agnostic.
Agnostic. What would you say, Tim? No, you're not here. I'm the one supposed to answer questions.
I don't often say this here, but I'm not an expert. But it is often true. So with regard to swoop, actually, where does the name come from?
The people in the company made that. Hyperfine, that name was something obvious. It's a physics term. The original name of the company was Hyperfine Research. I think Matt Rosen came up with that, but it's now called Hyperfine. Swoop, like something that swoops in. I actually think I did not have any role. I'm not in the company. I own a small, teeny-weeny 0.01% of the stock or whatever it is, some teeny, tiny amount. I founded it at the beginning and helped devise them in the early days, and now I sit on the sidelines and applaud. I think someone in the company came up because it evokes the quickness of being able to come in and do things on the wheels and be able to swoop in. That's my sense.
Kind of cool. Was the application to COVID patients actually, was that under the emergency authorizations?
I believe so. Again, I was not involved in that, but it was done, some of that was done at Yale Hospital, Yale Medical Hospital, Yale School of Medicine, and I believe so. And there are, obviously I was just kind of throwing out a few examples, but there's been a number of peer-reviewed studies of SWOOP's efficacy in various clinical settings. My, again, inexpert reading of those papers is that those studies are showing areas where it can be almost as good as a conventional MRI, other areas where it's clearly not as good, so that helps because of the lower spatial resolution or the different types of contrast you get, low and high magnetic field. Those sorts of studies help inform the medical community as to when the SWOOP system would be useful and when you wouldn't want to use it. So, as an example, because the signal levels, even with all the great engineering and making things work like a maser and all that sort of thing, the signal levels at low magnetic field are lower, the magnitude of the signals, because the spin polarization is lower. That ultimately, in addition to contrast, creates a coarser spatial resolution in the images. A kind of typical hospital MRI you might get at 1.5 to 3 Tesla magnetic field might give you about a 1 millimeter spatial resolution in the image. You see an image of your brain or part of your body, you zoom in, 1 millimeter. These SWOOP things might be giving you something like 3 millimeters, approximately. That's coarser. It's a little bit like using a 10-year-old iPhone camera to today's or something like this. Still can be useful, but the image resolution is as high. So, not surprisingly, if the features you're looking for in a person who has had a medical issue are large features, like there's been something happen to the head and they want to know whether there's a bleed, a so-called bleed, blood and or fluid have built up in the head. Those are usually, if they're there, large things that are centimeter or several centimeter scale underneath the skull, let's say, and they want to know whether it's there so they can maybe put a hole in the head and drain out the fluid or something like this to save the person's life or help them. Those typically with a 3 millimeter resolution, if it's a 2 centimeter object, you can see it no problem. And since the people you're looking at are typically in a traumatic situation who've come to the emergency room or something, rather than wait in line for the expensive MRI machine which is filled up, they might have a few swoops around to do some quick checks. That's the kind of thing where the clinical trials are tending to show it would be useful. However, other sorts of issues, some people, for example, who have epilepsy or other kinds of issues, it's known there can be very small lesions in the brain that have to be identified so that surgeons can go in and cut them out, and they might be 1 or 2 millimeter objects, and you want the highest spatial resolution MRIs to be able to find that. It might even get down to 0.5 millimeter. You don't want the 3 millimeter resolution thing, because it's going to be not only not finding that, but maybe finding false positives, which you don't want either. So proper peer-reviewed clinical trial type studies to figure out the use cases, which ones do and do not merit the use of this kind of technology is underway. In parallel, the technology is improving. They're using, believe it or not, AI technology, training on AI to be able to improve the sharpness of the images, and the hardware is getting better too. So maybe they'll go from 3 to 2 millimeter resolution over time, and the use cases will grow. That's why in that tagline on the headline of the Science article, it said MRI for all, but it said, could be amazing, but we had to make sure doctors are willing to use it, and that needs the clinical trials to study things well enough to show the use cases. All of us want things that are going to help, but we don't want things that are going to cause false positives or not be useful. Right now, SWOOP is just for the head. I'm told they're developing variations on the system which could look at other parts of the body. You could stick your things to the system now. You could, in principle, put limbs in. It's not FDA approved for that, I don't think, but I think it has that ability. But there's other, like looking at the torso and whatnot, they'll want to build variations like Swoop 2, or they'll come up with some other name.
So the question was, could you put
Yeah.
these in a football helmet?
Maybe not in the helmet, but maybe on the sidelines. It's inexpensive enough. And it is, on the order of approximately $100,000 to buy one and doesn't need a shielded room. Conventional MRI machines are amazing things, but they might be $1 to $2 million, another $1 to 2 for the shielded room, a staff of people. You need to have a staff of several people there all the time. These things maybe cost around $100,000, don't need a shielded room, don't need anybody basically can learn how to use it because on the iPad, they sent it to Africa with no skilled people, and the local doctors were able to get it going very easily. So if you get the cost low enough and it has enough utility and you want to see whether somebody's had it and the clinical trials show it's useful enough, maybe ultimately in clinics, not just hospitals, even ultimately in schools or something like that to check kids if something's happened, you got to get the cost down. So that's where it can go. But it's also just a mindset change. To date, previously, most people in this field, and that's not a criticism, it's just how it goes, had been thinking ever better performance. Cost, forget about it. Inconvenience, we don't care. Ever better performance, ever better resolution. That's the way we go. And that is necessary for some things, like finding those special lesions in a brain that might need surgery, right? But that's not the only tool. We don't only go for high performance. Sometimes we want things which are efficient and easy and good enough performance. Hence, you have a wonderful computer in your phone. You don't say, no, I only use supercomputers. Supercomputers only for me, right? Right? Actually, accessing the cloud, you are kind of accessing supercomputers, but okay.
I think we should go on a bit in spite of the hour with the questions. So we'll just move to diamonds. And
expensive? Do you want to know that?
Yes or no?
Do you think it's an accident that if you, hardworking fellow like Connor here, let's say, wants to buy a diamond for a loved one, that if he scrimps and saves, he can just barely buy a nice diamond and have all his savings depleted? Do you think it's an accident that that's just the prices of gemstones are tuned to deplete almost everybody's savings accounts, as opposed to be 10 times larger and then almost nobody could buy them? Or 10 times less expensive, and then it would be nice still, but it wouldn't be that big a deal. Do you think it's an accident? Or possibly it's been set by a cartel? Yeah. So there's a kind of cartel that maintains the prices, I used to steward here, to basically extract kind of the maximum money from people. Super wealthy people can do it, sure, but a typical person, right? It's like possible with some savings. So diamonds that are grown, so the gemstone thing there, we don't use gemstones, obviously, in this science work. They're more like and so those things are expensive because of the cartel to the left. The grown diamonds, laboratory-grown diamonds, which are, from a physics and chemistry point of view, the same as the ones grown out of the ground, just maybe with less impurities and more controlled, they're not trivial in terms of cost. It depends on what working with the growth companies, what details you want, like any sort of specialty thing. But in principle, they can be, tens of dollars each, $100, that kind of thing. And at scale, if these applications become really scaled up, then development will drive the cost down.
Tens or hundreds are for the little 4mm squares?
The little 4mm squares with high densities of NVs, which have been made state-of-the-art to do our super-duper science experiments, might cost on the order of a couple $1,000 because they're state-of-the-art things which are being done in a boutique, bespoke way by a company, right? It's a little bit like if you want a specialty thing built just for you by a machine shop, it's one cost. If you're buying one of 10 million that a factory is making, after all the economies of scale, the cost will come down. The real growth costs are limited by like the electrical power that they have to use. The actual cost of the methane and other things that go into it is trivial. It's like electrical power into running the machines and a little bit of the personnel for doing it. Maybe you can get it down to tens of dollars per diamond chip at scale if they really wanted to. Right now it's typically hundreds, and very specially hundreds for the one in the middle, a few thousands for the one on the right because it's this bespoke special thing.
So magnetobiology question.
Yeah.
So apparently, I believe we don't know all the reasons that organisms have magnetic sensors in them or the potential for magnetic sensors. But the question is, can you shed or can this research shed light on bird navigation?
Exactly, right. So that's one of the things we've thought about over the years and how talked about the magnetotactic bacteria. These are very simple creatures, and there it's clear that they use magnetic nanoparticles that you can actually see and right in there to give some forces and bias their swimming in a certain direction. They also have little cilia just as they kind of do their drifty kind of motion like that. But higher organisms like birds, there's strong phenomenological evidence that they use magnetic fields for navigation. But the actual biomechanisms are, as you just said, Tim, are still in debate. Some people think they know what it is or have evidence, others dispute it. We've looked into using, talking with biologists, using the quantum diamond microscope to explore those questions, and we almost did a couple experiments in the past, but we needed to see that we could really add value and that there were some signals we could really potentially measure. So to date, we have not. But other groups around the world using the technology have begun going into that field. So maybe, I think it certainly has the capabilities to add usefully. But isolating the source, the mechanism and something that you could measure has been controversial. So that's a Weasley answer, but it could.
Question about the Curie point, which is, do all materials reset at high temperatures?
I believe all materials at some point, if something melts, at some point it's going to not be a magnet anymore in the same sort of way. It may have some sort of interesting structure. There are Curie points that are associated with typical ferri and ferromagnetic materials. Some have more complicated multiple transitions as they warm up. There are many materials which aren't magnetic at all in this sense. They either can have induced magnetism that is aligned with the magnetic field, so-called paramagnets, as you know, Tim, or ones, the most common kind of materials, oppose magnetic fields. The electrons inside of the system react to magnetic fields in a way that make induced little magnetic moments that oppose the magnetic fields, and those are called diamagnets. But for the ferri and ferromagnetic materials, they will reset at some temperature. Yeah.
Any more questions from this crowd? Here's one.
Real quick. Can you hear me?
You're going to ask about the quantum Hall effect.
Well, actually, gentleman's question already answered, familiar. But I have personal questions. Some of you may have the SSD computer with no hard drive. One of the words is quantum tunneling. Confused me. Can you elaborate a little bit?
Yes. So let's see. Do we have some chalk? Okay, I'll use my hands. Remember when I talked about the wave-particle duality? Well, if you have a particle, let's say an electron or an atom, it also has wave properties and is described by a wave function that will tell you things like where, probabilistically, where the object is, maybe aspects of how it's moving. Aspects of the wave function would tell you things about its internal states, the electronic and nuclear spin, but the kind of basic wave function would tell you things about its physical location. And this would not be at one point necessarily. It would be a probabilistic distribution described by this wave function. To solve that wave equation, even if you place it inside of a barrier that has so the electron is inside of a barrier that has walls, my arms are indicating walls here, like between this region of space and that region of space. To solve the equations that Schrodinger first wrote down that describes the wave function as a function of position, you have to have boundary conditions at the walls which will have a non-zero, typically a non-zero amplitude of the wave function, even on the other side of the wall. So if it was just a particle in the box, it would be bouncing around. But because it's also a wave, the wave function will mostly be inside the box, but little bits will stick outside, the tails of this wave function will stick outside the box. Exactly how much depends upon the details. How thick are the walls of the box? How tall is the wall of the box? Other things about the electron or the atom inside of that box. But the fact that some of the wave function extends outside of the box is sometimes known as a tunneling. It's as if the particle, in this case, or the wave function is tunneled through the box. Another thing is you could say it has wings. It extends outside. There's some special cases if you have infinite barriers in which this won't be the case, but in practice, most things aren't infinite, right? And so there will always be a little bit of this extending out. So this is a fundamentally quantum mechanical effect. If things were truly a particle inside a box, it'd be inside the box unless you put a hole. But now it's in the box, but a little bit of it extends outside the box. And by box, it could be a location within a molecule or something like that, right? It could be an atomic scale thing, or it could be related to these defects in diamond that I described as to where the wave function extends. So, yes?
One thing that ran through my mind is the
Just a sec, Jeremy.
characteristics of a magnetic field in a high radiation environment, say in like a reactor core.
Yes.
Has there been any studies on that? I'm sure it has, but anything that you know about that?
Yeah, and so that's very good timing on that question, because one of the projects in my research group at the University of Maryland is funded by your tax money through the Department of Energy, is to explore the use of diamond magnetometers to operate in high radiation environments inside of possible nuclear fusion reactors that are being developed now. If fusion, right now the work on nuclear fusion, which you may have read about in newspapers and things like that, has reached the stage where they've just barely gotten to the point of producing more energy in the reaction in certain cases than went in, although to the reaction. If you take the energy to the whole building that's running the thing, the whole apparatus, it's still much more energy going in than out. So they're still even far away from being able to net produce more energy for the entire system than going in. But in the fusion reaction, they've recently gotten, the scientists have, to the point of being able to get a little bit more energy out than in. They'll make more progress and that'll get better. Okay, great. Let's say you get to the point where you're net producing more energy than you're putting in these science experiments. Now everyone's happy, and next stage you want to actually make a reactor. You know how reactors work, whether it's coal or wood or nuclear fission or nuclear fusion or whatnot. Ultimately, it's energy that's turned into heat that will boil some water in a steam turbine and use Faraday induction and all that sort of thing to generate electricity and power for all of us. But that means you need, if it's going to be a useful reactor, it's got to be operating pretty continuously. You don't want a thing that operates for a millisecond or a second and has a successful science experiment. You want something that's going to be operating for weeks and months at a time. Maybe every few months you got to go in and do a quick service operation or something like that. Brief operation is fine for physics experiments. It's not good for engineers who are developing a practical reactor. As you also may know, most likely, there are several approaches to fusion, but one of the most likely ways to make an actual operational reactor is to hold the plasma, it's implied in your question, within a magnetic bottle. What's a magnetic bottle? It's a set of magnetic fields which will take the charged particles which are undergoing fusion, and because charged particles moving around are affected by magnetic fields through Lorentz forces, keep them constrained in the space where the fusion reaction is going on so they don't leak out, go to low density, and stop fusing. But charged particles moving around not only are affected by magnetic fields, charged particles moving around create magnetic fields. And those magnetic fields will add with the magnetic fields that you're creating to make your magnetic bottle, and they'll be random, and sometimes they may cancel the magnetic fields, creating essentially a hole. The magnetic fields you applied and the magnetic fields they're creating may sum to something that allows the charged particles to escape. So how do you deal with that? You need to measure the magnetic fields, not just that you've created, but the other ones created by the roiling fusing plasma with a set of sensors, and then have a feedback loop and a feed forward, probably a mixture of the two, to be able to adjust and control, to keep that thing under control. That means you have to have, you see where I'm going, don't you? You have to have sensors which can survive inside a fusion reaction. The sensors they use now are simple and can survive long enough for these physics studies, but they will degrade and burn out pretty quickly as the fusion plasma eats them up. Diamond, as an extremely hard material where the carbon atoms are bound to each other, has a good chance to survive inside of a fusion reactor. And so that's why the DOE has given us a non-trivial amount of your tax money, thank you very much. Where does it go? It pays those hardworking grad students and postdocs, and we buy some equipment. Maybe pays for, well, they're paying for my trip here and things like that. And to do studies to see whether maybe down the road this technology using these defects in diamond altered in a way, because we can't do the conventional measurements, because the apparatus that we use, we can't stick those quantum diamond microscopes in there. The diamond might survive, but the other components would burn up. So we have an idea on how we might be able to make a so-called all-optical measurement that would survive inside of the fusion reactor, but it's still in the very researchy stage. That's good to be in the researchy stage now, because in practice, maybe 10 years from now, they'll be at the point of beginning prototype fusion reactor demos, and then 10 more years after that, if things go well, they might actually have these systems coming online and providing power. That's if things go well. Quite possibly, and not just with the magnetometers. The whole enterprise has to progress. Maybe it will never get there. Maybe it will. So that's the answer. So yes, absolutely. And not just in fusion reactors, but in other extreme environments where there's a lot of radiation or high pressure. One of the reasons we like the diamond so much is it's such a robust material. It can survive. It brings quantum out into the real world. We're taking quantum effects held inside of a robust host and bringing it out into the real world, not stuck in a cryostat or in a delicate vacuum chamber or something like that in the lab.
You answered my question.
So on those notes, let's thank Ron again.
Thanks to all of you. Thanks to the Walker family.